This lesson deals with supplemental problem 8.5. You can find this problem in the ECE202 ebook in the Chapter 8 Supplemental Problems on page 4. Given this circuit, can you find the value of I of t in steady state? We have a three-step algorithm for solving the problem in the frequency domain and then mapping it back into the time domain. So let's take our time domain circuit in step 1 and let's map it to the frequency domain. Our source is a times the cosine of omega t, where omega is 100. And the angle is equal to 0, so it's 8 at angle 0, and then our frequency is 100 radians per second. The resistors map as resistors. The inductance, though, is j omega L, so if you multiply this times 100, you get 2, so it's J2 ohms. Likewise here, j omega L, so 100 times this is 4. Likewise, same value here, 4 ohm resistor, minus j over omega c is the impedance of the capacitors. And they're the same value, and it turns out that minus j over 100 times 2500 microfarads is equal to a minus j4. The current that we want to solve for is actually the current coming in here in the frequency domain, and we could find that if we found the equivalent impedance looking back into this circuit. In other words, reduce this, called a ladder network, to a single impedance. Let's start over at the right-hand side of the equation. What I've got are two elements in series. So just like resistors, we'll do impedances in series by adding them. And parallel will take product over sum if there's just two impedances in parallel. All right, so 4 minus J4 is the value of the impedance looking back into the circuit between these two terminals. I'm going to call that Z1. Now that's in parallel with this capacitor, which is minus J4 ohms. So I'll take the product over the sum. So minus J4 times 4 minus J4 over the sum of those two. Multiply this out. So you multiply this times this, I'm going to get a J squared. I have two minus signs here, and then the j squared is a minus, so I get a minus 16. And then I've got minus j4 times 4, and that's minus j16. Do a little addition here. I've got 2 minus j4, so I get minus j8, and then just 4. Could divide through by 4 here, and that would give me minus 4 minus j4 over 1 minus j2. So that's the impedance looking back into the circuit from here, from these two nodes. I'm calling that Z2. Now that's in series with J4, so I'm just going to add J4 to that. I've got a common denominator here of 1 minus J2, so let's multiply 1 minus J2 times J4, and that's going to give me a J squared. 4 times 2 is 8, and then 2 minus signs is the plus 8. And then I've got 1 times J4, and then I've got this other numerator, minus 4 minus J4. Do a little algebra here. These cancel, and I have 8 minus 4 is 4 over 1 minus J2. Again, that's the impedance looking back into the circuit from here with these two terminals. That's in parallel with this inductance, which is J4 ohms. Now I'll call that Z4. So that's going to be the product over the sum. So the product of J4 with our last result, which is 4 over 1 minus J2, over the sum of those two. Multiply through by 1 minus J2. That gives me a 1 minus J2 here, and then a 4. Multiply then these two, so I'll get a J16, and then I get a J4, which is over here, and then I get a J squared. 4 times 2 is 8, and then the J squared gives me a minus sign, so I get a plus out of that, so I get 8 plus 4, which is 12. Divide through again by 4, and this is the impedance Z4, which is looking back into the circuit this way, between these two terminals. Now that's in series with 2 plus J2, so we're just going to add it to that. The previous result, J4 over 3 plus J, and add to that 2 plus J2. Let's find a common denominator of 3 plus J, so I'm going to multiply this times 3 plus J. So the 3 times 2 is a 6, and then I've got 3 times J2, which is J6, and I've got J times 2, which is J2, and I've got J squared times 2, which is minus 2. And then we're going to add plus J4. I can do some algebra here. I've got 6 minus 2, which is 4, J6 plus 2 plus 4 gives me J12. Multiply numerator and denominator by the conjugate of the denominator, so we'll make the denominator real. Be 3 minus J and 3 minus J, just multiplying by 1. So again, 4 times 3 is 12. 3 times J12 is J36. And then we've got 4 times minus J, which is minus J4. And then I've got J12 times minus J, which gives me a J squared, which is a minus 1, times another minus 1, gives me a plus J12. Then I get the real part squared, which is 9. I get the imaginary part squared, which is 1. Here, the inner product terms cancel. In other words, this times this cancels with this times this. So just get the real part squared plus the imaginary part squared. That's equal to 10. Numerator, I've got 12 plus 12 is 24. And adding these two, I get a plus j 32. So just dividing by 10, I have 2.4 plus j 3.2. I'm going to find the current coming in. That's going to be the voltage divided by the impedance. So I'm going to put this into polar form. So I'm going to punch that in my calculator. Get a magnitude bigger than either of these two. So 4 seems reasonable against the square root of 2.4 squared plus 3.2 squared. Again, square root of that is equal to 4. You don't want to do this by hand. You want to do this with a calculator that has a rectangular polar conversion. The angle is going to be in the first quadrant. We're going to be greater than 45 degrees because the imaginary part is longer than the real part. So this seems reasonable. So 8 divided by the impedance, the equivalent of 4 at angle 53.13 would be 2. 0 then minus the denominator of 53.13. To go back into the time domain with our third step, just simply put the cosine of omega t between the magnitude and the angle. Our answer for I of t in steady state is 2 times the cosine of 100t minus 53.13 degrees, and the units on this are amps. This is supplemental problem 8.5.